Hi, everyone. In this video, we are going to talk about the area of a region, how to do that by double integrals. So if you have RB region, the SY plane, then if you want the area of the region R, then all you have to do is to calculate the double integral of your region, but your integrand is a constant. They kind of illustrate as to why that gives us the area of a region. Well, recall that for a general region, you have written here that one variable is going from point to point, whereas the other variable is going from curve to curve. So to illustrate this example, I will choose y to go from curve to curve. But you can also do this with x going from curve to curve as well. Okay. So let's say this is the region of our curve. If that is the case, then taking the double integral of my region, dA, using our formula, that's equivalent to integrating from A to B, integrating from G of x to H of x of just a constant 1, but the order will be dy dx. If I evaluate this, first I integrate with respect to y, and if I were to integrate with respect to y, then because I don't have any variables inside, I'm integrating a constant, which that will become just y. Because my bounds of y are from the curves h of x to the curve g of x, then that then my inside integral will become integrating g of x minus h of x using fundamental theorem of calculus. So I am left with evaluating the integral from a to b of the curves g of x minus h of x here. And now that is something that we have seen before. This goes back to Calc 2, where we're now taking the area of the region formed by two curves. So area between two curves. And because in the end, we're taking the area between two curves, that is why we have our formula for the area of the region R just being the double integral of the constant 1 for that. And note that this works for general regions. And so because it works for general regions, that means it also works for rectangular regions. And so to illustrate that, I will go back to the example, the last example from 16.1. So recall, in that example, we calculated the area of a region R, which turned out to be a square with both length and width to be 2. Now, when we did this example, keep in mind that because it was a rectangular region, we were able to find the length and find the width and use our equation for area of a rectangle to get the area of the region. Well, now that we know our general area of a region equation, let's do that again. But now using our area of a general region equation to calculate that area. Calculate the double integral of just a constant. And because in this problem, my region is just going to be the rectangular region where x goes from 0 to 2 and y goes from 0 to 2. Rewriting this double integral as an irritant integral will mean I go from 0 to 2, 0 to 2, dy dx. Okay, so I integrate with y first. doing that, I will get the integral from 0 to 2. And the derivative of a constant will be the variable. And because it integrated with y first, that will be y, where I evaluate y from 0 to 2. Using fundamental theorem of calculus, if I plug in the upper bound, I'll get 2. If I plug in the lower bound, I'll take 0. The difference of that is 2. So I am left with taking the integral of 0 to 2 of the constant 2. That has an antiderivative of 2x. Evaluate that definite integral, and I get back my area of the region 4, which is precisely what we got when we did calculate this region back in System 1. So this means that our general area equation works overall. We can use this in rectangular regions as well. So now that we have this general equation, let's see how this general equation works for taking the area of a general region. So let's try that with this example, where our goal is I want to find the area of the region formed by the curves y equals x squared, y equals 6 minus x, and y equals 6 plus 5x, where I am told from the very beginning that x is non-negative. So my advice before we continue is let's go ahead and sketch what this region looks like. So first, let's go ahead and sketch out 6 plus 5x. So the purple line will represent y equals 6 plus 5x. I'll use the pink line to represent the line y equals 6 minus x. And then I will use teal to represent x squared. So this will be y equals x squared. Because my region R is the region formed from all these three curves, my region R will be given below. Okay. So first thing that we need to do is we need to find the intersections of each curve. And the reason why I need to do that is because, let's use green, because if I do that, then that will help me set up the region where the outside integral will go from point to point. And so for that, let's go ahead and do that. First thing I want to go ahead and note, for the two lines 6 plus 5x and 6 minus x, if you set those equal together, you will quickly get that the way they will intersect is if s equals 0. And if you want to see that, let's go ahead and illustrate that out now. So 6 minus x, let's set that equal to the other line. 6 plus 5x. Let's solve. Well, first you need to notice that the 6's are going to cancel themselves out. If I were to subtract both sides by 6, I'll get negative x, then it's equal to 5x. And then if I move one of them to the other side, I'll get 0 equals to 6x by adding both sides by x. And there's only one solution to that, and that is when x equals 0. So for x, I know that this point on the y-axis is going to be s value of 0. And we could quickly see, because the two lines are in slope-intercept form, that the corresponding y value, that would be 6, since that is the y-intercept of both of those lines. Okay. Now let's continue doing that finding the intersections of s squared with each line respectively. Let's first start by finding the intersection between x squared and cis minus x. Moving everything to one side of that equation. In this case, I'll move everything to the left-hand side. I will get x squared plus x minus 6 equals 0. Okay, that is a quadratic that we can factor, and we can factor that into s plus 3 and x minus 2. So now I have the product of two terms equaling 0. If I have a product of two things equaling 0, that means one of those things has to equal 0. So that means either s plus 3 equals 0 or s minus 2 equals 0. But that only occurs if s either equals -3 or +2. However, let's write this as s equals -2 or +2. However, I can quickly eliminate s equals -3, and I can eliminate s equals -3 because I am told from the very beginning that x is non-negative. So because x is non-negative, that means x equaling -3 cannot happen, meaning x equals 2 is the only solution I'm going to get. So this intersection will be s value of 2, and plug it into either cis minus x or x squared, you will quickly get the corresponding y value is 4. So another intersecting point will be the point 2, 4. And now let's repeat that process for the intersection between x squared and cis plus 5x. Just like with the previous intersection, let's go ahead and move everything to one side of the equation. I'll move everything to the left-hand side. That will give me x squared minus 5x minus 6 equals 0. Again, on the left-hand side, I now have a quadratic that I can factor in a straightforward manner. And the straightforward manner is factoring as x minus 6 and x plus 1. So I'll go ahead and do that. Okay, so now I have a product of two terms that equals 0. If the product of two terms equals 0, that means either one term equals 0 or the other term equals 0. So that means either s plus 1 will have to equal 0, which means that s will have to equal -1, or s minus 6 equals 0, which means s will have to equal 6. Again, I can rule out the possibility that x equals -1 because I'm told from the beginning that x is non-negative. Because I can rule out that possibility, that means for this corresponding point, my s value is 6. And if you plug it into either the x squared or the cis plus 5x, you will get to the corresponding y value is 36. So our corresponding y value is going to be 6 and 36 for that. Okay. So now that we have our intersections and we set up our curves, let's go ahead and start setting up this integral. The first advice that I would give is when you're setting up your region, I'm going to have y go from curve to curve, not x. The reason why is because given in this problem, I already have y written as functions of x. So keep in mind that when I do set up my region, I am going to have y go from curve to curve and x go from point to point because y is already written as outputs of functions of x. With that in mind, the one thing that I want to keep a note of immediately is the following. With respect to x, notice that going from curve to curve, with respect to y, I have two different types of things or types of orders for my curves. To the left of that dotted orange line, my lower curve is the line 6 minus x, and my upper curve is the line 6 plus 5x. To the right of that dotted line, notice that my lower curve is x squared, and my upper curve is 6 plus 5x. Sometimes when you have a region like that, you might have a case where your lower and upper curves might be different. And so you're going to have to take that in consideration for that. If that does occur, then what's going to happen is your region R is split into two separate regions that I'll denote as R1 and R2. Where R1 is the value where my lower curve is the 6 minus x, and my upper curve is the 6 plus 5x. And my upper curve is where my second region, sorry about that, is my lower curve x squared, and my upper curve 6 plus 5x. Because of that, my region is split as the union of two separate regions, which I'll denote as R1 and R2. So let's go ahead and set up R1. So in R1, we already specified that x is going to go from point to point and y is going to go from curve to curve. Based off of my intersections that I have, the smallest x value that I have is 0, and my largest x value that I have is 2. So going from point to point in the region R1, x is going from 0 to 2. Now in R1, y is going from curve to curve. The smallest curve with respect to y is 6 minus x, and the largest curve with respect to y is the curve 6 plus 5x. So because of that, we have that. Okay, and with that, again, as stated, my lower curve is 6 minus x, and my upper curve is 6 plus 5x. So now I have R1 set up. Now we repeat that process for R2. So in R2, again, x is going from point to point. So I asked the same question of what is the smallest x value and what is the largest x value? Well, given the intersections that we found, we have that the smallest x value is 2, and my largest x value is 6. So if x is going from point to point, x is going from 2 to 6. So because of that, in R2, s is going from the point 2 to the point 6. And now, writing with respect to y, we have